And so I ran it by my other course, and it seemed to be somewhat helpful. So we'll talk through it as well, just to get you an idea of what's happening. So pretty much everything we've done, and goes all the way back to partway through exam 2, is just conversions. We aren't doing anything fancy. There really is very little chemistry content behind it. It's just conversions. Right? There is some chemistry content in interpreting formulas. There's some chemistry content in interpreting equations. There's some chemistry content behind gas-volume relationships, between mole-volume relationships, and whatever the hell a mole is. Right? But that chemistry content, unfortunately, for better or worse, doesn't really even need to be understood if you do dimensional analysis. If you don't do the dimensional analysis, then you have to have the conceptual understanding of what that means, and that is very, very difficult for most students to get through because we can't manipulate those structures in hand. Okay? So, what are we doing? It's conversions. Okay? The format that we're using here is dimensional analysis. It's also called the unit factor method. Other people go through and say, well, it's just comparisons. Ultimately, it's all the same thing. We write down what we want, okay, our desired unit, then what we're given, and then, if we have to, we'll initiate some kind of conversion in between. And that may require multiple steps. Okay? And this isn't new to you. When you woke up this morning, what did you do? Why? Why? Why do you need that caffeine? Right? Why do you need that chemical energy to start your brain? You got things to do. What are you doing? School. Okay, let's pick class today, and staying awake in class today was the goal. That's where you're ending. That's the desired system. Where did you start? You woke up and felt like crap. So what did you do? You started a conversion to get you crappy mood into awake mood by rocking out to obnoxious music. By drinking coffee, by getting fed, by getting water, getting hydrated. All of those are conversion steps to make sure that you get to the desired goal. Okay? Everything we're doing is what you do in your everyday life. We're now putting a formal notation behind it. Right? The other part to it is we can quantify it in chemistry and in math class. Right? What's your quantification for not falling asleep in class today?
Consequences.
So it's just whether you did or didn't.
Yeah, it's just whether you did or didn't. Did you fall asleep? No. Success. Right? Or did you fall asleep? Yes. Success. Right? Either way, there's no real quantification of that. In chemistry, we're concerned about quantifying it so we can replicate results. Okay? So we need to come up with a numerical system behind it. So when we look at our measurements and quantifications, we're going to take a numerical value. I'll actually write that out. So we'll take a numerical value, and what are we going to tie that numerical value to? Okay, a unit. Okay, so you need to consume 35 milligrams. Of what? So when we're looking at that quantification, I have a numerical value, I have a unit. But I also need something else. What else do I need? A substance. The whole point of dimensional analysis is to take that numerical value and the meaning associated with it, the unit and the substance, and convert that unit and substance into something else that has meaning. Right? The process of doing that does change the numerical value, but it doesn't change its aura, if you will. Its soul is still trapped within that system. All we're doing is converting how we interpret and visualize and measure that value. Right? So dimensional analysis is now focused on the unit and the substance. Right? How can we convert the unit or the substance? We would need a conversion factor. Okay, give me a conversion factor. 2 to 1. What does 2 to 1 look like? In fact, I can even help that out a little bit better. Okay, 2 over 1. I'm fine with that too.
2 over 1, what the? Right.
Okay. 2 over 1 is a numerical value. Does that change anything about the unit or the substance? No. The numerical value is absolutely useless if you don't know what it means. That's the unit and the substance. Okay? So 2 over 1 is not a conversion factor. 2 over 1 is a numerical value. I don't want a numerical value. I want a conversion factor.
2 units of substance over 1 unit of substance. It's a different substance.
Okay? We can do better than arbitrary units. Cups. What do you want to convert those cups to?
Good morning.
Okay? Is good morning something that's useful?
Energy.
Okay? We could go into grams. How are we getting grams from this? We would need to know that relationship. That numerical relationship would be something that we would have to define. Okay? If we didn't define it, where do we get the numerical relationship? From somebody else who defined it. Okay? We're constantly finding those relationships, and if we don't define it, we have to rely on somebody else. Okay? If we don't all agree to the same conversion system, what happens to our relationships? Okay? If I now talk about cups to grams, is my cups to grams the same as your cups to grams? No. There has to be a single accepted system. That single accepted system is what you need to know and what you need to be referencing. Okay? So when we look at our systems or all of our calculations, we have the numerical value, we have the unit, and we have the substance. Okay? So we could try and do cups to grams. Okay? We could also try and convert, say, milliliters into, what's an accepted system to convert milliliters into? Liters. Okay. Where do I find the conversion factor, the numerical values that now belong to that?
We're supposed to have it memorized in powers of 10.
You're supposed to know the powers of 10 for the milli and know that this is 10 to the third. Sorry, let me fix that. Minus third and 1. You need to know those numerical systems. Okay. Can this be 1 milliliter of, let's try this, blood equals 10 to the minus 3 liters of, why not?
No.
Why are you saying no?
Because it needs to be the same substance, the substance.
Okay?
The substance is changed.
The substance is changing. Okay? Well, is that relationship weird? Why is that weird?
It's connected.
Is urine in your blood? No. Okay? We would need a conversion factor to relate those two. Okay? I'm changing the substance and the unit. I can't do that. I can only change one at a time. So I can convert the milliliters of blood into liters of blood. Thankfully, I can't convert it into urine because that would kind of suck. Okay? At least in how we've envisioned our world, that would kind of suck. Okay? Both because you pee blood then and you'd bleed urine. Both of those would just be weird. Okay? So that's what our mathematical system, what our scientific system is trying to do. Take these numerical values, take the unit system, take the substances, and come up with ways to do those conversions. You're responsible for knowing some of those conversions, like the milliliters to liters. Okay? How about the conversion between grams to AMUs? You're saying no, you're not responsible for memorizing that. I kind of mostly agree with that statement.
You should know where to get it.
Periodic table does not convert grams to AMUs, which is the other part of where we're going to get it. You should know where to get it. Where do you get it? It's the front of your exam. You look at the front of the exam and it shows you that 1 gram, or it tells you that 1 gram, technically, of any substance equals 1.66 times 10 to the minus 24th. I blame you for making me memorize that, by the way, of a substance, because everybody wants to use this conversion factor. Right? Oh. So I blame you for fixing me when I'm wrong. 1.66 times 10 to the minus 24th grams of a substance is 1 AMU of a substance. Right? How useful is that to memorize? Did I memorize it? No. Right? Very easy to get it swapped. This is why you have it on the exam. Use the exam. Take advantage of it. Right? So let's try another one. I want to convert the grams of a bike into grams of frames. Technically, no. What's the relationship? What's changed? The substance has changed, but where do we find the relationship between that substance?
Chemical formula. You need the chemical formula.
We would need the formula, the recipe for how you built that. Right, what is that recipe? How many frames make 1 bike?
1 frame.
1 frame, 1 bike. Now that you know what each of the individual relationships is to convert the substance, you could then go through and convert the mass, or convert the grams. We can't just convert the substance through. I have to make sure I'm in the entire measured unit system. Okay? Both the unit and the substance to convert. So this isn't an invalid conversion factor. It's converting too many different things. What could I convert to? Well, I could convert that into units of bikes. Okay, what is our unit? It's the single one. It's the count. The number of grams of a bike equals the number of bikes generated. Okay? The unit just being a piece, the whole thing. Okay? That is very often implied in the term bike, and we don't have to say units of that substance. Why is it implied? Okay, if we went around and said, I want that unit of pen. Please give me a unit of paper. Okay? Adding that word now makes it kind of confusing. Okay? Why do we add that word when we move to chemistry?
Because you need to make sure units cancel in chemistry.
It's a clarity of what we're referencing. If I said sodium chloride, what is my unit?
Atoms. Or molecules.
Right? It ends up becoming atoms. Okay? Would atoms make sense for sodium chloride?
No,
Why not?
because it's a molecule.
Atoms refer
An
to-
atom is a single element. Sodium chloride is not a single element, it's a molecule. So this is where chemistry is now adding terms. We now have to know that the unit of bikes is now a molecule of sodium chloride, is an atom of sodium. We're adding that term to help clarify that we understand what sodium chloride is. That's it. Right? Where would I find that conversion factor? I could go to the periodic table, potentially, okay? And this is the part that we need to be good at. What does the periodic table give us? It is our table of elements. Keep going. What else does it give us? And you might think in response to what we're trying to find here.
And you?
The mass per unit of our atom. Right? What is the mass unit that the periodic table gives us? Grams, not true. AMU I'll accept, but AMU gets a little bit weird. What is an AMU? An atomic mass unit. So when we look at the mass value, the atomic mass on our periodic table, the number underneath, that is written as AMUs, which is a random weird mass unit that we have no way of measuring per an atom. Right? So the full unit is AMUs per atom. That says molecule. That says gram. Okay. So I could add up sodium and chloride, what is that, 23 and 35, 58. Right. What would the unit on that be? The atomic mass unit per molecule. Not an atom now because there's 2 atoms that went into it, so it's now a molecule. AMU related to molecules. What does this conversion factor relate? Grams to molecule. What does that mean? Okay. We don't have a direct conversion between grams and molecules on the periodic table. Okay. We have a conversion that relates AMUs to molecules, not grams to molecules. This conversion factor is invalid. So we would have to try another conversion factor. How do we want to adjust this expression to get a conversion factor? Okay, we could switch it to looking at our molar mass. What unit are we changing? Grams or molecules? We'd be changing molecules to moles. Now what I'm looking for is the grams related to moles. Where is that found? Run back to the periodic table. It's 58. 58 what? Grams for 1 mole. The units are now matching the system. I have access to that from the periodic table. You're not explicitly told that like you were with the grams to AMUs. You have to be able to interpret it. You have to be able to recognize where that information is found. Okay? Lots of people are struggling with that. So what I would recommend you do is write down where that information is found and what units are there. Right? So this slide shows up way later in the slideshow, so if you want, you can pull it out and look at it. It's right towards the very end. Okay? But what this is saying is, how do I convert between atoms or molecules of A to AMUs of A? Okay? I can use the periodic table. AMUs to grams. Okay? Grams to moles. Okay? It's providing general locations on where you can find things. This would be a big, long thing that you could go through and memorize. Okay? We have another example. Same deal. It's in your slides, just way late. Okay? Individual measurement systems, you're required to know from Unit 2. The number of atoms, how do we convert between those? Okay? We can convert substances by looking at the subscripts of a formula. Molecules or atoms, we can look from balanced equation. Moles, okay? Formulas or equations or units or Avogadro's number. Okay? These are all things that you need to have access to and pull from. Okay? So when it comes to the exam, we have that first sheet, that first page. The front page has your name on it, and then it lists a bunch of conversion factors. I listed most of them on the right there. The second page shows the periodic table. For the first exam, we had drawn on arrows, right? Okay, which you should go back and make sure you remember those arrows and what they mean. Okay? Here's some more information that I would recommend you do. I would pick probably thorium in this case as my representative element to take a look at, and not any of the others, because all the other ones we're more likely to use. Thorium being in the F block, probably not going to get tested on, so I can draw whatever I want on or near thorium, and it's not going to mess up my ability to use the periodic table. Make sense? So, if I wanted to zoom in, make it a little bit bigger, thorium, 90, 232.0. What did the 90 mean? Okay? We could go through and call this the atomic number. That is not wrong. That is technically correct. And if you were asked a specific question about atomic number, you now know where to find it. It's written on your exam where you wrote down that extra information. What is the atomic number, though?
Number of protons.
The number of protons. You can now answer a question about the number of protons quickly and easily. All you got to do is look at the sheet where you wrote down what it was, where it's found. There's no question. There's no interpretation in your brain. It's there. Okay? By seeing how frantically everybody's writing, I'm guessing you already knew that one and you're trying to keep it in your brain. Good luck. Next one. What is 232?
Atomic mass or molar mass.
Okay. It is typically known as our atomic mass, but it could also be written as our molar mass. What are the units from either of those?
232.0.
232.2 is not a unit. That is a number. I don't care about the number. I didn't ask for the number. I want the unit.
AMU or
Okay. AMUs is potentially valid to come out of this. AMUs to what? To atoms. AMUs to atoms of what? What's the substance? Right? 232 ties to which of those? AMUs or atoms? The AMU. So there's my number.
Look, we do have an AMU difference.
To atoms. We do not have an AMU to grams. Or, sorry, are you looking at the...
Yeah.
Yeah, that is on the front of the exam. What is our molar mass? Pause. Is AMUs to atoms ever going to be useful in the real world?
Not really.
Why not?
It's too small. No one cares about that.
We can't manipulate single atoms. So even if I invented an instrument to measure AMUs, I don't have the control over a single atom. It's going to be a useless measurement system. Okay? In a lecture class, would that be useful? Yeah, because what we're going to ask you to do is convert between AMUs and atoms. Why? Because we can. Unfortunately, that's the way it is. Okay? So, what was the more useful unit system to work with?
Molar mass.
How about the molar mass? What does the molar mass relate unit-wise?
Mass.
Grams per mole.
The grams to moles of what?
Thorium, the substance.
Our substance being thorium. Why do we know it's thorium?
This is the TH.
We're looking specifically at thorium. That's why it's all boxed in. What are the numerical values that get tied to these?
Avogadro's number.
232 grams gets tied to
One.
1 mole. This is not Avogadro's number. What is Avogadro's number?
Moles to atoms or molecules.
Okay. Avogadro's number is that 6.022 times 10 to the 23rd. 232. Is that 6.022? No. So as soon as you hear Avogadro's number, it better have 6.022, and then a bunch of other stuff that you don't care about. Look through the rest of the information on the front. What do we have? 6.022, 10 to the 23rd, items, mole. That's Avogadro's number. So now when you go through to solve a question that you're trying to find a conversion factor between grams and moles, you're like, I don't remember where to get that. Maybe that's on the front, oh, that's Avogadro's number, 6.022. You can then pause and say, what did I write down on the front of my exam? Where it shows grams to moles. Oh, I wrote it down. This again goes back to I didn't see anybody writing this information down. Cool, you can keep that in your head. And when you use Avogadro's number, I'm just going to cry. Because I'm kind of at that point. Okay? That's where that information is. So that's now useful. You've got that space on your exam. You can purge that. You don't have to think about it. You don't have to keep it in your brain. You just use it whenever it shows up. Okay? That's useful. Okay? Unfortunately, I don't have a whole bunch more white space on this, so I'm going to have to erase that and provide some more stuff that I would consider useful on the exam. I want to be able to figure out how to convert between substances. I want to go from substance A to substance B. How can I make that conversion? Where would I find that information? Periodic table. Point to the periodic table where I can find the relationship between nickel and copper. I can find nickel in a box, and I can find copper in an entirely separate, independent box. Is there a relationship between them? No. Useless. That's why we have boxes. Bad idea. Try again. How can I find the relationship between A and B?
Convert them both into moles. Or convert the...
So a unit system, I could use moles. Okay. Moles is really just our unit. Okay, a really large number of that unit. That doesn't give me the numerical value.
What are you trying to compare?
How do I convert between substance A and substance B? What information do I need to be able to convert those two things?
The unit.
I have a unit. I have a substance.
You need the numerical value of the mole.
Where do I get that numerical value?
Or molar mass.
Okay. Molar mass. Let's start with that. Molar mass. Molar mass relates moles and grams. What's our unit? Moles of A, moles of A. Molar mass doesn't work. A couple people were starting to, I'm going to say it like it's bad, mouth off, but I don't think you were trying to mouth off. I'm just saying you were mouthing the words. Okay? Saying something about a chemical formula. Like if I had the formula A2B, how would I convert A and B? Where would I get those numerical values? Periodic table gives you moles and grams, atoms and AMUs. This is moles and moles, not the periodic table. Literally, what did I just write? The formula that says A to B. What does the 2 mean? There are 2 A's for every 1 B. The chemical formula gives me that relationship. It's there. If I write that down, now when I get on the exam and I say, oh, I've got to convert substances. Oh, the unit I want is moles. Convert it to moles. Where do I get the numerical value to do that? Oh, that's from the chemical formula. You have that information now specified. Does it have to be a chemical formula?
Yes. No.
Okay, and again, I'm out of space, so I'll clean some of this up. We're talking chemistry now, by the way, so that's why it says chemical. What is the relationship between A and B?
1A for every 1B.
For every 1A, I can react 1B. Where did I get those ones from?
The coefficients.
The coefficients from the chemical equation. I have an example again that allows me to tie and pull that information in. Okay? By pulling and providing these examples, you now have a way to find that information. If this is written down on the first page of your exam, within the first 5 minutes of the exam, you will likely not forget these relationships. If you decide to wait until when you need to use them, you will likely forget those relationships and end up using a myriad of other conversion factors. Okay? Probably the most likely conversion factor that I'm going to throw in as a multiple choice answer for these, somehow using the periodic table, because I've already heard periodic table suggested as an answer 4 or 5 times today incorrectly. So I will be using the periodic table to generate wrong answers. Okay? Write this down. Okay? Are there other conversion factors that we talked about last week?
Oh, keep, slipping a line. Can't you convert milliliters to moles or something like that?
Ooh, there's an interesting one. Is it possible to convert liters, I'm going to give you a hint there, liters, into moles,
Molarity.
okay, of a substance, okay? If we were looking at a solution, okay, solution may not be a tip-off. Maybe you want to see AQ next to it to help you out. I can use something known, oh, come on. Sorry, let me erase everything, or attempt to erase everything. Okay. Liters. Moles. Substance, whoops. We're looking at a solution. This would be aqueous. Moles of our solid or a substance within that solution. Where do I find that relationship between liters and moles?
Molarity.
Our molarity. Okay. Our molarity represented as capital M. If I put a numerical value in front of that capital M, let's say 3, where does that 3 show up in my expression?
3 moles, there's 1 liter.
3 moles, 1 liter. I now have a way to show the relationship between liters and moles. Liters of an aqueous solution, moles of the substance in that solution. I don't have to memorize what molarity means anymore because it's written down on my test because I wrote it down. Okay. Is there another conversion factor, which is where we're about to move to? Gases. I can look at liters of solution and relate those, liters and relate those into moles. Why might this be confusing? What's molarity showing?
Same thing.
The exact same thing. What are we talking about now when we look at our liters to moles? This is for a gas. If I'm looking at a gaseous system, I can convert liters into moles. What is that conversion factor? 22.4. Dang it. This is why you would write it down so you don't forget it. 22.4 liters is 1 mole. Okay? As long as we're a gas, as long as we are at STP. Okay, which we addressed. STP is stupid. This conversion factor is stupid, but you're told to memorize it anyway. Okay? Why are you told to memorize it? For the same reason we have the AMUs to atoms conversion factor from the periodic table. It's another conversion factor that you can go through and use. Okay?
As long as it's STP.
So as long as we're at standard temperature and pressure, we're okay to use this. Okay? If you're being asked to convert liters to moles in this class, you are. Yeah, let's just say that. Okay? If this is now written down on your exam within those first 5-10 minutes, you don't have to memorize any more content. The rest of it is application. So stop going through and staring at flashcards memorizing, because hopefully you can just cram memorize for 5 minutes. Right before the exam, you can shove your fingers in your ear and just go la 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 la, I'm not listening to anybody, here's your exam, purge. Okay? Vomit all that information all over the exam, the information, not breakfast, and then take the exam. Now it's a question of applying it. Have you been doing the practice to get you through it? If you've been doing the practice, you should be set. Okay? It's the problems that you need to be focused on. So, with that, our ideal gas behavior, we had all of those rules that go behind them. Yes, that's your chemistry content. Those things are important to know. Okay? The big ones out of this would be the no volume. Molecules have no volume in a gas, and they have no attraction for one another. Right? I would argue those are the two biggest concepts to come out of your gas laws. The rest of them are also important, but I think those are going to be the most relevant. Okay? The no volume one's the biggest. Okay? Because the no volume one is probably the biggest reason that that expression now becomes valid. 1 mole of any gas equals 22.4 liters. That means when I switch from hydrogen, what can you tell me about hydrogen as far as its volume goes? What do you mean it doesn't have any? Are you saying ideal gas behavior it doesn't have any?
Right.
Okay, back away from ideal gas behavior.
It's very, very tiny.
It's very, very tiny because
It's only got the,
One electron.
it only has the 1 electron. Its size is dependent on the number of electrons. Okay? If I compare hydrogen gas to, what do we got? Radon? Radium. Let's do radium.
radium's bigger.
Radium is bigger. Why is radium bigger?
It's got a bigger nucleus and more.
I don't care about the nucleus. It's got more electrons. Those larger electrons means the atom is bigger. Which means if I put 6.022 times 10 to the 23rd atoms of radon and atoms of hydrogen into the same container, okay, or try to put them all together, would I expect the radon to occupy the same volume as the hydrogen? No, because radon's bigger. And yet what does our first rule of ideal gas behavior say? No volume, which means they are the same, which is why this expression is now valid. Okay? It's because of that volume being kind of neglected. Not neglected, ignored, negligible. Negligible might be the better description. Okay? And that relationship we're now required to use. So, use it. And we had a guy on the team that was not usually of the most right mind whenever he'd fence. And the first time he'd go down the strip and try to stab the other guy, he'd miss way to the right. He'd lose. So then he'd start again and he'd go way down the strip again, attacking the guy going crazy, go way to the left. And he'd start up again. And before he started, he'd say, this time, aim for the middle one. 1, 2, 3. That's how you need to move. Okay? If you want the reasons behind that, you can talk to me after class, but I'm not recording that part of it. Okay? 1, 2, 3. Right, left, middle. To the right, what do we need to put down?
Leaders.
Our goal.
Your end state
Okay.
hydrogen.
So in this case,
Liters.
our unit was liters, and then hydrogen gas. Okay, here's our chemistry. What is our substance?
H2.
H2. You have to remember that hydrogen is a diatomic molecule. You have to remember the nomenclature behind that. What did you start with?
2.0 grams.
Okay, I'm going to complain about the 2.0. What did you start with?
Grams of hydrogen gas.
Grams of hydrogen gas. The numerical value associated with that now, 2.0. Okay. Aim for the middle. We've now got it trapped. It can't go anywhere. We just have to make sure it works. The ideal situation, we would take grams of hydrogen gas and convert to liters of hydrogen gas. Okay? And we would go back to the front of our exam. That's cool. We can write that. We have erasers. That's cool. We go back to the front of the exam and we say, where does it say anything about grams to liters? It doesn't. Okay, so I can't go grams to liters. I need to convert the grams into something. Right? Our first step for pretty much everything that we're going to go through and do is get it into moles, because the moles is the central unit we can convert out to pretty much everything. So if I convert that into moles, I'm now good. Okay? Do I have the ability to convert between grams and moles? Yes, because I've written it down on my exam. I know that the number underneath my symbol on the periodic table is the grams in 1 mole of that substance. So I can look up hydrogen, and on the periodic table, there's my number underneath, 0078, because that's what our table gives us for some awful reason. Okay? That is the mass for 1 hydrogen, or 1 mole of hydrogen atoms. What do we have? 2 hydrogen atoms per mole-ish. So we need to multiply that number by 2.
It's just 2.
2 is good enough, point some numbers.
Sig figs 2.0.
Fair enough, I'll accept that. That's a much more scientific answer than me just saying some numbers. 1 mole of H2. I now have a new conversion question where I want to get rid of the units of moles of hydrogen. I already forgot what I was converting to.
Liters.
Thank you for the reminder.
Liters height.
Liters of hydrogen. Where do I find the numerical relationship for that? Again,
Conversion on the front.
I go back to the exam where I wrote down that information, and I know that that relationship, because I'm looking at a gas, needs to be
22.4 liters.
22.4 liters is 1 mole.
Yeah.
I can now punch it through my calculator if I wanted, or I could recognize that 2 divided by 2 is 1, and my answer becomes 22.4 liters. What was your assumption? Your assumption was valid. I completely agree. It was a good assumption to make. I didn't want you to not make this assumption. What was your assumption?
Well, I got 44.8 over 2. See, there's a whole other step we skipped.
Well, you said that.
No.
You just canceled out
Two,
the
two.
2 and the 2. You skipped a step.
Right, so now you're doing conversions in your head.
Get out of here.
I'm not doing conversion in my head. I'm doing the math in my head. 2 over 2. What did we assume? And the assumption is in that purple box.
That we are at STP.
That you are at STP.
What you told us.
Okay? And that you're a gas. The gas one isn't that far off because it says gas. Okay, so that assumption was probably okay. It says STP. That's the only time that's valid. Does our question say at STP?
If it doesn't say not at STP, you can assume you're at STP.
I would love to agree with you. In a textbook, yes. In the real world, no. Okay. So you would have to be careful on that. Okay. If it's written on an exam in this class, you can assume STP. Okay.
If we added at STP to our answer,
Sure.
that would make
That would also work.
That may not be
And that may not be an option if it's multiple choice. Yeah. Okay. Questions about that? How do you guys feel about the conversion? Everybody get that? I will say, for my part, that it looked like nearly everybody had that right, which is making me cautiously happy.
And then you get to the next exam, 30%.
Okay?
Oh boy.
you're greatly underestimated.
Okay. So let's work through this one together because this one's a little bit longer. I just want you to see the longer process. Okay. So again, right, left, middle.
Liters.
What's that? It should be in the slides. It's probably behind a white box would be my guess, so it doesn't show up. It's on that same slide.
Here's hydrogen.
So our final answer, we want,
Liters of hydrogen.
we don't want just liters, we want liters of hydrogen.
H2.
Right? We are running under the assumption that it's H2 because we would have to say hydrogen atoms. Right? So we have to make that assumption that it's hydrogen gas, H2. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? Step 2, what's the given information?
You gotta solve the chemical equation, right?
We'll come to that. What's our given information?
Oh, yeah. 2.0, or we have grams hydrogen gas.
That's what we want, liters of hydrogen gas. What are we given?
Grams
Grams of aluminum metal with dilute.
Grams of aluminum metal.
Fun equation. Not the top one. Yes.
Sorry, is that top one getting in the way?
Yes.
Why don't we need that?
What do you mean, why don't, we're given that? It's not, that's just given information. What's the numerical value given with that?
0.165.
So we have our left and right. We now have to figure out how to convert. So the very first thing we could go through and do, and this is where you can start to do things by inspection, grams of aluminum, liters of hydrogen. We're changing the unit and the substance. Am I allowed to do that? No. All right. So first step, when in doubt,
Moles of a
mole it out.
Oh dear.
Math it out? No, come on. Where do I find the conversion between moles of aluminum and grams of aluminum? Periodic table. Was it 27? Close. Oh, fine. 26.98 grams of aluminum is 1 mole of aluminum.
Are we skipping the whole chemical equation thing?
We're only bringing things in when we need to bring them in. Okay? At any point yet, have I tried to convert substances? No. I haven't. So wait. I haven't attempted to do that yet, so I'm not going to worry about it because that could be extra work. If it's extra work, why do it? Okay? And I'm not saying you're wrong in trying to do that, because what's the next thing we want to do? Liters of hydrogen, that's not a valid conversion. I want to convert the substance. How do I convert the substance, Paul?
You gotta screw around the chemical equation.
I need the chemical equation.
Right.
Okay.
so balance.
So we're now trying to convert the substance through moles, because I'm allowed to do moles in my system, because I had that on the front of the exam. What numbers would I put in there? As a hint, do not say 1 and 1.
Wait, what? No, it's not balanced.
Is it 2 and 1? Really?
It's not balanced. It's not a balanced
Okay,
equation.
it's not a balanced equation, so we would need to go through and balance it. So I'm not sure where you got the 2 and 1 from. Kind of confused me.
1 Al plus 1.
So we need 3 chlorides.
2 hydrogen.
This would be weird because we'd get 3 halves, right?
Yep.
Yep, so we can't do that.
So do more. Do 6.
If you need help with the balancing, talk to me after class, but that should balance it out.
I finally understand.
H2, I need a 3, 2 moles of aluminum. Mole of H2 to liters of H2. Oh, can I do that? Oh, yeah, I can do that. I can use that by making what assumption?
Gas. Gas.
That the H2 is coming out as a gas. Is that really an assumption?
Not really.
No, it actually says in the equation gas and I'm at STP. 22.4 liters is 1 mole.
So when you assume that it's at,
It allows you to do that calculation. Okay? The only time that you really, so there's 2 cases in when you shouldn't make that assumption. Case number 1, it's the real world. The real world, there's too many people saying what standard is, and it's just different. So you can't make that assumption in the real world. Okay? The only other time you can't make the assumption you're at standard temperature and pressure is if it says the temperature is 400 degrees Celsius.
Holy cow.
Or it's negative 20 degrees Celsius. Because both of those temperatures are
Impossible?
not standard. I said degrees Celsius, both of them are valid. They're not standard temperature. So you need to remember what standard temperature and pressure are. Is that something that you might want to write down? Yeah? Okay, what's standard temperature? 0 degrees Celsius, standard pressure. 1 atmosphere. Those are the 2 big ones that you would need to remember. Okay? 0 degrees Celsius, remember, could get spit out in a bunch of other ways. Usually the bunch is only one other version. 273 degrees Kelvin. Okay? Atmospheres, as we'll see in I think the next slide, there's a billion units for atmospheres. Okay? And you're like, there's no way there's a billion. Yeah. Yeah, there are. It's stupid. Okay? We now have our unit systems converted across. We have to enter it into the calculator, and we would have our final answer for the liters, what was it? Liters of hydrogen gas. Okay? Each of those conversion steps is something you know how to do. It's now a question of stringing them in. If you've got where you can do those conversions on the front of your exam, it's now just a question of looking that up. Okay? So, what is pressure? Pressure is just the force exerted by each of the gas particles. Remember, they're constantly moving. Okay? If something is moving and it runs into you, do you know? Okay? You usually feel that. Okay? That pressure or that force is our pressure. Okay? It now comes down to how do we measure that. Okay? It's kind of a neat device. We won't get into it too much. You can use something like this, some derivative known as a manometer, which is kind of fun to say. It's like that song. Yeah. All we need is Fozzie. I should put Fozzie Bear up here. What? Actually, I don't know. It may not actually be Fozzie. Regardless, if we take a dish full of liquid, and then I take a tube that's closed at one end and fill that with liquid and then invert into the liquid dish. Okay? Gravity is going to pull down on that liquid, right? Yeah, so it's going to want to fall. What's going to prevent it from falling?
Pressure.
Something would have to push back up. What's pushing up?
Atmospheric pressure.
Atmospheric pressure is pushing down on the outer dish, preventing the liquid in the tube from coming out. It is the counter effect of gravity on the liquid and atmospheric pressure allowing us to monitor the pressure of the gas around us. Okay? There are a variety of variations of this, but that's ultimately the origin for all of these. So when we look at measuring pressure, what we were really concerned about is the height of that liquid. Okay? So the standard unit for pressure, or the typical unit, most common origin unit, is millimeters of mercury. Why millimeters of mercury? Because when we did this, there were that many millimeters of mercury above the bottom of the container. As pressure changed, we saw that level go up and down. Right? So we established, well, I think this is standard pressure, so I'm going to call this my standard pressure. Here's my 0 point, or it's not even a 0 point. Here's just my standard pressure. That's what it was. Okay? So it's an observation made that we then quantified by taking a measurement. Okay? An important concept that comes out of this is the vapor pressure concept. Okay? So if we go back to this. What do you guys know about ether or chloroform?
Tastes like copper.
They taste like copper. That's interesting. I didn't know that one.
It knocks out people and
They knock out people. How are they knocking out people?
replace the gas.
One of the large contributions is replacing the oxygen. We lose the oxygen, we lose consciousness. Okay? There are other chemical issues there, okay? But it's the gas. Okay? That's a large contribution. So if you take nitrogen gas and put that over someone's face and just let them breathe in nitrogen, they will pass out. Okay? Because you're not drowning them, suffocating them without giving them oxygen. Okay? So they will pass out. Okay? Why is chloroform or ether a bad liquid to use for this system?
It takes a while to replace the oxygen with chloroform.
I'm not talking about knocking people out. I'm talking about putting chloroform or ether now as the liquid in this manometer.
Because it's less dense. You want a dense liquid for that.
It evaporates. What are we talking about when it evaporates?
It turns into a gas.
Turns into a gas. What happens, remember, this has to be open to the atmosphere. If I pick a liquid here that evaporates quickly, what happens to the amount of liquid at the bottom?
It evaporates less.
It evaporates, it disappears. Is there now anything pushing the liquid back up the tube? No. So the liquid in this tube has to be something that does not transition into the gas phase easily. Okay? This is why we picked mercury, because mercury is a metal and has insanely strong attractive forces between the individual particles, which is why it stays as a liquid and not transitions to a gas.
It's so safe.
Okay? And it's awesomely safe to work with. Okay? What we're referencing in this case is and that was sarcasm, just in case people missed that. It's not safe to work with. The vapor pressure concept. Ether and chloroform have a really high vapor pressure. That means if I just take a look at the liquid sitting on the counter and I measure the force exerted by the gas in that container, ether and chloroform have a lot of gas there. So they have more particles hitting the side of the container, which means more force or more pressure. So the vapor pressure goes up. Mercury, on the other hand, does not transition into the gas phase at standard temperatures. So what happens?
Stays the same.
It stays a liquid. Is there any vapor pressure then? No. Okay, so what we're looking at is the ability for a liquid to transition into the gas phase. It does not always happen at the boiling point. Okay? That's when we officially get a full transition. Okay? But we have evaporation as a general process, and in that case, there are some particles that will transition into the gas state. Mercury has such a low vapor pressure that we aren't concerned about it. Okay? The vapor pressure will increase with an increase in temperature because it has to do with particle motion. The hotter it is, the more likely your particles move, the more likely you'll have a gas, which means the more likely they'll impact the sides of our container. Okay? What if we try to do the reverse as just kind of a sidebar on this?
High pressure will dissolve the gas into the liquid.
Why do I want high pressure to get the gas into the liquid? Okay? High pressure means I'm forcing all of those particles closer and closer to each other, making the particles look more and more like a liquid. So increase the pressure.
Decrease the temperature.
Okay? What should I do to the temperature? I'm trying to dissolve, right? When I dissolved solids into the liquid, what did I do with the temperature? I increased it. What am I going to do with a gas? Why do I have to decrease it? Why is that? It's an exception, right? I'm changing.
Because the colder something is, the slower it's moving.
Look at the transitions you're trying to do. Solid to liquid. You're trying to break forces, which means add heat. Gas to liquid. You're trying to increase forces, which means take away heat. Right? There's not an exception. It's looking at what's happening in your transition. And as long as you address what's happening in each of those transitions, you can predict aspects of pressure and temperature. Okay? Just a neat little observation, which then takes us into our pressure, units of pressure. Like I said, there's a billion of them. Okay? We have atmospheres, we have inches of mercury, because of course, millimeters of mercury is the standard unit, but we have the American unit, right? So we have to deal with inches of mercury. Centimeters of mercury, because why not? We have millimeters, why not convert it into centimeters? Okay? We could do decimeters, we could do feet, okay? We could do quarter inches. We don't have a quarter inch, but whatever. Okay? We could do any length measurement we want of mercury, and we would have a conversion factor to work it out. Okay? So that's where we're getting the billion possible conversions. Okay? After that, we run into torr. What the hell's a torr?
It's the ugly guy from the
Okay? Torr is coming from somebody making this observation and saying, I don't want to change my unit system. I named my unit system after me. I'm not changing it to a different system. Everybody has to use my unit system. Yep. PSI. American, pounds per square inch. Right? Super American, right? It's like cubed American because you got pounds and then square inches. Okay? KPA, kilopascals. Okay? Pascal, because the guy that made his observation on pressure said, I'm not changing my unit system, you change. Okay? Unfortunately, in this case, all the people that invented different unit systems for gases, no one was stronger than anybody else, and so instead of only having one or two to worry about, we have all of them to worry about. Okay? Because they all survived. Okay? Sort of. I think they're all long dead, but beside the point. The other part that comes with this is that each of those have different reasons for why we would use that unit system. Okay? Pounds per square inch is typically what you're looking at your car in. We wouldn't look at atmospheres. Okay? Because you're looking at a slightly different system, you change the unit system that you're working with. Why? Because everybody hated you. Okay? And me, for that matter, because I don't like it either. Okay? So, you're now responsible for converting all these, right? Wrong, don't worry about it. Just know that you need to be able to do it.
Oh.
Okay? There are 3 variables that affect gas pressure. What are those variables? Temperature, volume, and the number of molecules. What happens if I increase the temperature? What happens to the pressure? Okay. The pressure goes up. Okay. What happens if I increase the volume? If I increase the volume, what happens? The container's now really big. It's less likely for those same particles to impact the sides of the wall, which means your pressure goes down. Number of molecules. I put a bunch more molecules into the system. I'm going to increase the number of times molecules impact the sides of the container. My pressure goes up. Okay. We could go through and find ties between temperature and volume, the number of particles and volume. If I increase the number of molecules, what happens to the volume? If I increase the number of molecules, what happens to the volume of the container?
It stays the same.
When I blow into a balloon, what happens to it? It gets bigger. Okay, what did I do by blowing in it?
Now we've assumed the container's variable.
The number of molecules increased. What happened to the size of the container?
Not bigger.
It changed. So our volume does change. Yes, we are making some other assumptions. We are making assumptions about the other variables not changing. Okay?
So we
That
can't
is
just
an
put it in a tank.
important observation. If we looked at just a container that now had no potential for volume change, when I breathe more molecules into it, what happens to the volume? It stays the same because what did I start with? A container where the volume doesn't change.
Pressure goes up.
Okay? So something else would have to change in regards to that. So what people went through and did is noted that all of these things were interrelated to each other. And they were interrelated to each other through a constant. Okay? Which is kind of an interesting statement to make. They noted that when we tied all these things together and put them into plots, that they all varied with a constant. Okay? What does that then mean? I can then define that constant. P and V should make sense. Those are pressure and volume. T, temperature. The number of molecules, N. Why do we call it N? Because M, oh, I'd never thought of that. Because N for number. Neat. Good job. The number of molecules is our N. Okay? The number of molecules, more than likely we're looking at very large numbers of molecules. That large number of molecules is very likely to be moles. Okay? We now have this nifty little relationship where R is now defined to be a constant. Okay? And I used to remember it really well, and I'll probably screw it up. But let's see, 0.08211.
Yeah, no. Oh, well, only one, but yeah. At least some.
Okay? What are the units on pressure? Oh, there's a million different units. Which unit do we use? Atmospheres. What is the unit on volume?
Liters.
Liters. What is our unit for moles? That was a dumb question, sorry. What is our unit for temperature? Kelvin. Why do we use Kelvin?
Science.
Because we're scientists.
Degrees Celsius has a positive and a negative, which would mean if I pick different temperatures, what's going to happen to the R? I'm going to get positive and negative values for constants. That doesn't make sense because it's constant. By definition, what happens to constants? It doesn't change. Right? So regardless of what the temperature is, the moles, the pressure, and the volume will somehow counteract or contribute to make sure that R always comes out to be 0.08211 atmospheres, liters, moles, Kelvin. What is R now? Yes, it's a constant. I'll accept that. Keep going.
R unit.
It is a conversion factor. I can now convert atmospheres, liters, moles, and temperature all with each other. Why is this conversion factor so much more challenging than other conversion factors?
Because there's 4 units.
There's 4 units that are getting converted. Units?
You know,
This plugs into your calculator super easy though.
Right.
pops out
So-
units.
You can graph this.
Where this can come in handy, though, is we will now only largely do our conversions within this format. Okay? So we end up using just this one equation. Wait, did Mike just say that there's an equation that we can use? Yes. Yes, I did. Remember that equation. When it comes to gases, that's what you use. The part that's important, your units have to be in atmospheres, liters, Kelvin, and moles. As long as your units all line up, this system is lovely, beautiful, and perfect, and you can use it as much as you want. What if your units are in degrees Celsius? Well, then this doesn't work, and I got to throw it all out and start again. Convert your degrees Celsius into Kelvin, plug it in. Okay? What if your atmospheres are in pounds per square inch? Convert it to atmospheres, plug it in.
Does this table, is that gonna be on?
So as far as what's on the test, those are all now conversion factors. 1 atmosphere equals 29.9 inches of mercury, and you'd be like, well, do I have to have that memorized? No, you don't have to have that memorized. Does that mean it'll be on the exam? No, it won't be on the exam because you won't have pressure conversions on the exam. Period. Period.
We only have one more exam and then the
Okay.
final.
So what is R? R is our gas constant. Notice that I wrote 0.08211, and up on the slide I got 0.0821. What was our conversion between Celsius and Kelvin? 273.15, right? Remember? That's what I had remembered. Remember when we talked about that? I happen to remember an extra string of numbers after it. I happen to remember that there's an extra 1. Okay, that's it. So 0.0821 is all you need because that's your 3 sig figs. Okay? R now gives us this expression that I can do all sorts of nifty conversions from. Okay? I can solve for the pressure of a given system if I know the moles in that system, the temperature of that system, and the volume of that system. I can figure out the pressure. Cool. I can figure out the volume of that system if I knew the other 3 variables. Okay? That's the power of it. We're allowed to convert them. Okay, but what happens if I start with something and now I change it?
For example.
Okay, for example, let's see. Actually, I'm not going to do an example. If I'm given a gas at conditions A, pressure, volume, moles, and temperature, and I now increase the temperature, okay, everything else stays the same, okay, or most of everything else would stay the same. This goes back to kind of Paul's suggestion. If I breathe more molecules into a container that cannot change its volume, other things have to change. So what ends up happening is I'll look at a system, right? Say a closed container. There's my closed container. And I'll put some more molecules in there. So I have starting conditions of A, and I have now conditions for the number of particles of B. But this is now like Paul's container. The volume doesn't change. I have my starting conditions for volume A. Let's go ahead and do it. Temperature A and pressure A. If my volume cannot change, what is my volume at conditions B?
The volume stays the same, but your temperature and pressure are going to increase.
Okay. My volume stays the same. But now I go through and say, actually, Paul, I don't like your example. Temperature stays the same.
So your pressure has to increase.
So the pressure will have to change to compensate for that. How much does it compensate? Well, that's going to all depend on how many molecules I put in. I'm going to put in twice the amount I started with. What is the moles of B? It's not the moles of A, because I said I put in twice.
Double.
What can I now go through and do?
You said volume staying the same.
I said volume stays the same, temperature stays the same, pressure now changes. What happens to the pressure?
it increases.
It increases. How much does it increase by?
Times 2.
Double. In theory.
So some people are really good at seeing those relationships. Some people, like me, are not. So for those of you like me who are not, let's work through this. R is the same for both conditions, right? So we have that expression. Okay. What do I know NB is?
Well, we know the,
NB.
oh, NB. It's 2 NA.
Whoops, that was supposed to be an eraser. Yeah? What is temperature B?
Same.
What is pressure B? I don't know.
We don't know.
What is volume B?
Stays, volume A.
What happens to volume A?
Stays.
It can cancel. What happens to temperature A?
Cancels out.
Okay. How can I get 2Na to the other side of the equation? Multiply both sides by 2Na, right?
Right.
What expression do I get? 2Na PA over right? What happens to the NAs? They cancel. What happened to pressure? Twice the amount we started with. I don't even have to know what the amount I started with is. I now know the answer is twice the amount. Okay? Some of these relationships become intuitive. That's where you get the names of the Charles law, Boyle's law, all that fun stuff. You smash them all together and you get this PV equals nRT expression that allows you to do all those relationships. It's pretty sweet. It's pretty awesome. It's also a relatively limited aspect of our exam. Okay? So on Thursday, what we're going to do is look at the moles of neon gas that occupy 2.34 liters at STP. We will solve it two ways. After that, we're going to skip into looking at probably limiting reactants, right? Which is going to be where you get to prove to me how much you understand this material.
Go back one slide.
Just a sec.